Hello, can you hear me now? Okay, sorry about that glitch. Okay, it's not called Stark at Home for nothing. It's sort of an informal thing. And I apologize for this glitch. So welcome everyone to another Stark at Home episode. And this one is going to focus on computational integrity. If you're interested in learning more about, so this episode is not going to have almost anything in the way of math and stuff like that. It's going to be quite informal and basically compare 5 different competing solutions. Some of them are technological, some of them are less, to this basic problem of computational integrity. And of course, one of these 5 solutions is related to the Stark proof system and to other proof systems. So we'll get to that at the very end. But I want to discuss the general problem. And this is also an answer to the question, what is it exactly that zero-knowledge proof systems deliver? What do they solve? What problem do they solve? What good attribute do they deliver? And what other things deliver that thing? So for those who are joining for the first time, I just want to point out that there is an Ask a Question tab at the bottom, and you're very welcome to use it and and ask your questions there. And then from time to time, I will go there and sort of answer some of the questions. Most of the time, I'll be less. I won't be able to view the chat because most of the time I'll be using my Scribble pad and not seeing what people are writing. So if you have a question, and I will pause from time to time to answer questions, please use the Ask a Question tab. Okay, so without further ado, let me go into this screen and start with the question of what is integrity and what is integrity and what is computational integrity. So a famous quote by C.S. Lewis that I used is that integrity is doing the right thing even when no one's watching. And of course, this leaves open the question of what is the right thing and what is doing. But I think we all have a good understanding, informal and sort of intuitive understanding what does it mean to operate with integrity. And indeed, this phrase captures it pretty nicely. And so the term, so one of the terms that was offered by Skulitz was that computational integrity, let me just offer it because I also said I will, is that, so Skulitz said that computational integrity is doing the right computation, knowing it will be verified. It will be verified, which I like very much. And sort of it speaks, certainly it talks about things that also Skulitz is interested in. And we share the same passion of using proof systems for making sure that a computation is doing the right thing. But I prefer a different definition, the one that I offered, which I'm not sure it's exactly capturing the spirit of it, but it is, updating the state of your system, updating your state, as you could put here either God or, the laws of nature, or think of some, very good, benevolent being updates the universe. So we all believe, I hope, or most of us believe, we live in the scientific age, that if we, if someone will drop a rock from, a certain height on the face of the earth, even if we're not watching, and the rock will fall at a certain speed and acceleration that are determined by mathematical laws and are sort of deterministically defined. And I'm here not going into quantum mechanics and stuff like that, right? But at least at the sort of classical level, nature is quite deterministic and operates in a way that is always the same and according to certain rules. And computational integrity means that we would like to be in a case where the state of the computations that we are running are updated in a way that is very much like nature would update the universe. So if we handed over the computation or the state of our system to, again, God or to the laws of nature or to some benevolent creature or being that is completely trustworthy, we would like the system to be updated in a certain way, the system with all the data that we have, the finances, the forensic data, the health data, everything about our, information and personality. We would like these updates to be maintained and updated in a way that is godlike in this sense, okay? So this is what computational integrity informally means. And I want to say that, so here's a slightly, more formally, more formal. So we assume that we have a certain state. So this is the state at time 0. And we also assume that we have a program. And I'll say in a few minutes, what do I mean by this program? And this program is supposed to receive inputs, right? They're supposed to be, so this is some computer program. And we're supposed to receive some inputs that come outside. And these go into the program together with the state. And there's a correct transition to a state S1 that we should move to. And then this process repeats itself again and again, right? That from state S1, we move to state S2. And we would like it to be the case that even if we're not watching, and even if someone with an incentive to move the state in a different manner, we would like the state to still be updated in a manner that is, godlike or behaves like nature behaves even when we're not watching it. So just like a rock falls at a certain acceleration and speed, we would like programs to be updated correctly and not, having things behave in ways that are not sanctioned by the program. So we're going to make several simplifying assumptions in our discussion here, mostly about the program and the input. So first of all, we're going to assume that there's one single program that is the one that updates the state of the system. Now, this isn't a strong assumption because you could think of, let's say, an operating system or some program that calls a bunch of other programs if the need be. So it's simpler to think of one program that dictates how the state should be updated, assuming a certain set of inputs. The second assumption that we're going to make is that there are no bugs. Now, of course, this is an unrealistic assumption, but I just want our discussion to focus on, something that is essential to this discussion. So we're not going to deal with the case of bugs, even though all sufficiently complicated programs do have bugs. But let's just neglect that and assume that we have a program that is indeed without bugs, and we're just going to expect, or we want to live in a world where it is updated with integrity. And the third assumption that we're going to make is that, this program is fixed and we're not updating it. And this, again, is not such a big simplification because at least at small enough periods of time, we do have a fixed program that is maintaining the state of the system. And then maybe once in a while we update it and then it's a different program. But at least that, in fine enough scale and looking up close, we can think of this as a fixed program. Finally, I'm going to, maybe at the end, but for now, let's make an assumption that, inputs are we're not going to deal here with the way the inputs arrive and are sequenced. So are sequenced correctly. And this is a huge problem that touches on things like front running and, what is fair and not, and who arrived first, and if there's a queue, who goes first. And certainly in the context of, decentralized systems, it's a big problem. But I want, at least for now, to assume that we're not going to deal with it because I want to look at just the other stuff. And then if we have time, we'll also go back to these things. So what we have is one fixed program that is the program that is supposed to update the state of our system. So we have this one fixed program. It's a single program that's supposed to dictate the update of the system. There's this stream of inputs that come, and from time to time, we want to update the state of the system, maybe after each input or transaction. And we would like to be in a world with computational integrity. So we would like to do this with computational integrity, which means that had this been the program that runs the universe and God is executing it, we know that it would have behaved in a certain way. And we would like to be in a world where all computations, even when they are not run by God or by nature, they have the same property of being correct. So this is the problem we would like to solve. And I'm going to mention 5 different ways to solve this problem, and then we're going to go over them and sort of discuss the various attributes of them. And I'm just going to mention these 5 different ways or technologies, if you will, for solving. So how to ensure computational integrity. Right? That's the topic of our talk today. How are we going to ensure this? So one method that I want to talk about is going to be called naive replay, and it says that every user in our universe is basically going to run the program that everyone else cares about. So everyone's going to read the inputs and run the program. The second is going to be reputation-based. So we're going to rely on reputation and have a small subset running the programs and inspecting the programs being executed on behalf of us. So this, we can call it delegation or delegation of accountability. We're going to have some accountants and some regulators. Accountability. We're going to have some special people that are in charge of maintaining computational integrity on behalf of the public. The third technology, and this is already a technology that's quite recent, is what is known as a trusted execution environment. So going back to the laws of physics, and why is it that we believe that if a tree falling in a forest that no one observes is going to fall in the same way according to the laws of physics? Well, we trust the execution environment that is nature to do always the right thing. So a trusted execution environment is some sort of hardware piece that we assume cannot be messed around with and must execute the program exactly as said. So it's some hardware technology or assumption. The fourth one, which is quite recent and gets a lot of attention within blockchain world, is fraud proofs, things like optimistic rollups. So optimistic, they also go by these names, rollups. And this is a method that involves game theoretic incentives and various games to deal with it. And the last one is what we're going to call validity proofs, or sometimes these are known as ZKPs, zero knowledge proofs. And in particular, this also contains things like Starks, which is the stuff that we at Starkware and I myself am very deeply interested in. So, and to state up front, I'm of course very biased. So I'll say up front, I like these best. but I'm biased. I like 5 best, but I'm biased. So, okay. So now I'm going to stop and ask see if there's some questions, and then we're going to go and just describe in a little bit more detail each one of these technologies, and then also describe what are their assumptions, what could go wrong, and how much resources does each one of these different technologies cost, society or whatever. Okay, so I see there's a question. Let me just So the question is, Mickey Latowitsky is asking, so C is not having bugs? So the question is it the case that computational integrity is synonymous to the statement of operating a program that has no bugs? So the answer is no. When we talk about computational integrity, we are assuming that we have a system that we're working under the assumption that the program that we would like to use to update the state of the system is the correct program, right? A different challenge is taking something that, at a high level we think is the correct way in which a system should be updated, and then converting it into code and maybe even to a something that runs on a specific piece of hardware. That's a different problem. It's a very big problem. Ultimately, it involves things like the undecidable halting problem. So it can't we mathematically know that it cannot be satisfactorily solved or resolved, this problem of eliminating bugs from a program. But it's a separate question from the question that we are dealing with here. The question we are dealing with here is the following: assuming that we have nailed the program correctly. So the computation we have in mind is indeed specified by a piece of code or by a certain piece of hardware, and we're going to assume that this is the correct program. We still have the issue of, we would like to entrust this program in the hands of someone. Maybe it's not us, and maybe that someone may be incentivized to misreport the output or to move the system to a state that isn't the correct one. And there are many cases that such a thing could happen. Maybe this is a system of accounts on a blockchain or in a bank, and then someone who's operating this system has an incentive to move all of the funds from the different users to one account, which is his. We would like this not to happen. This would violate computational integrity in most cases, assuming not all users have decided to transfer their funds to that person. So we would like to prevent such things. And if a system is operating under computational integrity, it is a system that is operating correctly, as if God were running it, or nature, or something that is very trusted. Okay, so so now I'm going to go back and we're going to dive a little bit into more detail into each one of these 5 technologies. And again, I'm reminding you, please use the Ask a Question tab here to ask your questions from time to time. So let's go over the different technologies, and then we'll also compare them in terms of resources and how they match up against each other. Okay. Okay, so we're going to start with number 1, which is naive replay. So what does it mean? Those of you who know blockchains should be very familiar with it, because this is really how blockchains work. And this is also how we check grocery receipts, or are supposed to do so, or check our spending every month. So what we do is so let's fix some notation. We're going to have n users in our system, and then it's going to be something very large, like let's say 10 billion users, like the number of people on Earth. So these are the number of users. Now, and then we're going to have a certain computation, and t is the amount, the size of the computation. So this could be the number of transactions or payments. This could be, the length of the computation that the whole system is supposed to be operating and doing, okay? So t is the size of the computation. And under naive replay, what happens is that we have a certain state of the system, state 0, and there are these transactions coming in. So there's, or this input is coming in. So input 1, and then input 2, a whole bunch of inputs, input M, and let's also use D for the size of the inputs. So that's the amount of data that comes in from time to time. So D is, so I mean, T is at least D, right? But T could be much greater than D, because we need to read at least each bit of the data. So we need to do at least D steps in our computation, but maybe each time we read some piece of input, we need to do much more. Okay, so we have these M inputs. The total size of all of this data is D. And now what happens is that everyone maintains the state S0 and computes the state S1. So we have n users, each one of them runs a computation of size t. So the total computation that everyone is doing, so the total amount of computation across all of the system, all of this universe, equals t times n, because each one of the n users needs to run a computation of size t. So it's quite large, right? Everyone is doing the same computation or checking that the system is okay. But now for this particular system, so this is a very safe method for dealing with computational integrity, because really, if anyone is cheating and someone is trying to move the system to a state S1, then every user observing this simply will see it and notice and say, oh, call this person out. You've done, you haven't operated with integrity. And basically, even if everyone but for me operated without integrity, at least I'll know that. So this is a very safe method, but it is very costly. And you'll notice here that blockchains really pretty much operate under this. And the reason blockchains today have rather limited scale, measured by the number of transactions per second that they can process, is really because they operate under this method of naive replay. They want everyone in the world to be able to hold the system accountable. I often call this inclusive accountability. So you want everyone to be able to hold the system accountable. And because of that, you want everyone to be able to inspect everything that's going on. So you want to limit the amount of computation, because otherwise people won't be able to use their laptops in order to follow what's going on and check that everything's okay and naively replay all transactions. And if they won't be able to do this, then slowly the system will devolve into one that is more reputation-based, which is going to be the next item that we're going to discuss. So just summing up, naive replay is a very old method. It is a method that we probably also use when we are checking the receipts that we get, or when a teacher is grading exams. It is also the one used by blockchains. It works very well. It's very safe, but it is costly. Okay, so now I'm going to pause and ask if there are any questions about this. I'm just going to see for a minute. And if not, we're just going to go on and discuss the second method, which is actually very, very efficient and has been used a whole lot of time throughout history. Okay, so let me go on to the next method. The second method is, let me use a different color. So let's call this reputation. Also known as banking, governments, etc. So another term is the conventional system. Now, in preparation for this, I was listening to a very interesting talk by the famous economist, Nobel laureate Paul Krugman, who is very critical of things like blockchain. And at least he was 2 years ago. It would be interesting to see what he thinks of them these days. But his basic argument was that reputation-based systems are what the world has evolved to accept. And reputation is a very powerful mechanism. It is also one that is based on game theoretic principles. You can think of reputation as being this repeated game. The reason the banks are not stealing our money and operating with computational integrity is because as much as they could benefit now from wiping out our accounts and moving it to theirs, they have a lot more to benefit from being trusted and from people repeating, coming to them repeatedly and entrusting them with computational integrity. So that's the principle of reputation. Now, reputation has been around for millennia, and it certainly is quite efficient. So again, if we have our end users, and we have T is the amount of computation, and D is the amount of data, we're going to have another number, which is A. That's the number of auditors. So what's going to happen is we are going to have a subset of the users. So A is going to be much, much smaller than N. Let's say A is going to be, I don't know, like maybe 1,000. So these are, these are the accountants, the lawyers, the regulators that are coming in and inspecting the system and holding it accountable. So we delegate accountability to these people. And now the way the system accountability. Okay, so the way the system now works is that the amount, there's one, let's say the bank does, T computation because it is the one, so some central trusted party is running some big computation. The auditors are also running the same computation or something similar to it. So the auditors run A times T computation because they also have to inspect pretty much everything, if we really want them to inspect what's going on. But the users do nothing, compute nothing. And this is very, so this system is very efficient because, we can't update our system without paying at least T steps of computation. And here we're paying something that is not much greater than T. It is A times T, which is, right, A times T is much, much smaller than N times T. There's another aspect that's really good here, is that it maintains privacy. Let's explain this. If, going back to naive replay or think about blockchains, if everyone is invited to inspect the whole system, then there's no privacy, or privacy gets very, very much compromised. Whereas in this system, really only the bank or the trusted party sees the data, and the auditors also see the data. So the users don't see all of the data. In this way, you can also maintain privacy. So that's another good thing. The downside of it is that it is prone to corruption. It is prone to stagnation, meaning that if someone comes from the outside, I mean, right, there's a very asymmetric situation here in which, who gets, the auditors have a lot of power, right? So how do you become an auditor? The auditors have a lot of power and the bank has a lot of power. So they control a lot of stuff. So, I want to be the bank. How do I become the bank? Or I want to be an auditor. How do I become an auditor? And then because the bank and the auditors are entrusted with a lot of financial value and other things, what if they collude to violate computational integrity? So there's also an assumption you have to trust the bank plus the auditors. And that's unfortunate. So that's a downside. So we have to trust them. And indeed, we all know of situations where things do not operate with computational integrity. Again, compare this to the situation with nature, where somehow the tree falls always according to the same laws of physics, no matter who's doing it and where, without any auditors yeah. So here we have to trust the bank and the auditors, and sometimes this trust is not really maintained. Okay, so we have covered the first two mechanisms and see their pros and cons. Okay, there's a question that I'm going to answer now. So the question is by Bent. I guess that not everyone will agree on what the trustworthy person, God, nature, etc. would do. Seems like introducing those words could be distracting. What do you think of just saying that the computation should be done in a trustworthy way that is agreed upon by the participants? Sorry for this slightly off-tangent comment. Yeah, I guess when I'm using, God or nature, I'm just trying to, it's just this one word that is supposed to capture the ultimate trustworthy, ideal computer executor, right? Often in cryptography, people talk about the ideal model and the real world model. So the ideal model is what I am referring to by the words God or nature, but maybe I'm going to start using the word ideal model as instead of something that is slightly more contentious. Okay, so thanks for this comment. Okay, so we covered two of the technologies, and now we'll go on to the third. By the way, it's very interesting to think about this this criticism of a lot of the standard economists, and as phrased by the venerable Paul Krugman, right? Why? Says Paul Krugman, why are you taking a technology that human beings have taken, millennia to perfect, which is reputation-based, and now you're essentially, with blockchains, taking a step back and going to this naive replay that is vastly less efficient? What value? You're taking a system and making it far less efficient. What is it that you're gaining by this? And that's a very good question that I encourage you to think about. There are a bunch of good answers, maybe at the end, that I can think of some, but I encourage you to think about this, because this is, for those of you who are coming from the blockchain world, right, this is a question that ultimately we together have to answer to the world at large. Why are we moving from the reputation-based system that is very efficient to one that is far less efficient, because now everyone is doing naive replay? And one of the answers I think we can give Paul Krugman and the standard economists is that, well, there is a way that is not reputation-based, and it is far more efficient than naive replay, but still does not have any trust assumptions. And of course, that's going to be solution number 5, but we'll get to that. So you could have all the benefits of the naive replay world, which is a very safe method, without the cost inflicted by it. And I think that's going to be a very good world to live in. So let's go on to technology number 3, which is the trusted execution environment. So trusted execution environment, or sometimes called T. And here you can think of things like most recently SGX, which is a piece of hardware by Intel. Previous to that, we had various trusted platform modules, TPMs, and probably a bunch of other things. So here the assumption is that, so just like we had this ideal functionality that I called it other names previously, and we sort of completely trusted to operate only as the program dictates. What if we had this amazing piece of hardware that is somehow guaranteed? It comes with a lock around it, right? And it's like really, really strong and hardened, and no one can peek inside. And and it even has sort of encryption when you send things inside to it. So all the data goes into it encrypted. The programs go in encrypted. The data goes in encrypted. Only inside this enclave, people talk about enclaves. So inside this enclave, which is completely, it's like this, I don't know, Faraday cage. Nothing can come in. Nothing can go out other than through the ways that are allowed. Inside this thing, you have some chip. And the chip operates completely as it should. And then there are signatures on outputs, basically, that say, this chip executed the program and asserts this is the output, or let's call it S1. S1 is the new state. So this is the trusted execution environment. And let's see now what happens. So you can have one party running the program inside this enclave. So running T steps. You have very good privacy because no one but this party. So privacy is really great privacy. So that's really a big benefit because you can send your inputs in an encrypted way. No one but the inside of the chip will see it. You have really good. So the rest of the world, the users basically only have to verify the signatures, which is very, very lean. It's much, much less. So the total amount of work is n times something that's really, really tiny. It probably is something like the logarithm of t, because you need the security to be at least the logarithm of t. But all the other users have to run something that is exponentially smaller than t, and this is still safe. So this is a great, great system. But the main issue with it is that we have to trust the hardware manufacturer, because it all relies on the fact that inside here there's some secret key that you use, a secret key that is used to sign statements. So if this secret key, and this secret key must be placed by the hardware manufacturer. So you have to trust the hardware manufacturer to not be compromised and not leak these secret keys. And also you have to trust that the no one can break the enclave. Let's say so maybe the hardware manufacturer was very trustworthy and didn't leak any of these secrets or reveal them outside, but maybe there is a physical process, because if you get this physical chip, then somewhere inside its atoms, the secret is encoded. So maybe there might be the secret key. And once you have the secret key, you can sort of extract it and you can decrypt stuff. For instance, the privacy gets ruined, and you can also ruin integrity because you could sign on any statement, even outside the chip. So you have to also assume that no one can break the enclave and learn the secret. And the problem is that this is very unlikely and extremely unlikely in the long term. And the reason is because of just the laws of physics. So, if there is some physical representation to the secret inside here, and now imagine that you're building a system, let's say the whole financial system of today, now its security resides on trusted execution environments. So you have trillions of dollars, trillions of dollars whose security relies on the assumption that no one can extract these secrets. So first of all, there's a single point of failure, which is the hardware manufacturer, right? And now maybe someone there may be bribed or corrupted to reveal these secrets. But even if not, maybe it only costs a few $1 billion to devise a physical process by which you can extract the secret. So it's extremely unlikely that this is safe. And indeed, for instance, TPM was, broken, and SGX, there are a number of attacks already mounted on it, but that already show that you can find things leaking out from the chip even without fully breaking it. But, we know for a fact that it is physically possible. I mean, there are atoms that somehow, or magnetic fields or something that somehow represent the secret, and they lie inside each one of these chips. So there is a way to extract it, and it just doesn't stand to reason that with sufficient funds you can't extract it. So that's the problem with this method. Okay, any questions about it? Okay, so I'm going to describe now two more methods that are now very much at the center of blockchains today. So let me just say that, first of all, there has been a period in which SGX was touted as a technology for blockchains, because you can sort of have a blockchain where if you want computational integrity and you don't want to trust any central party or any banker, you could just trust the hardware. But these things have not picked on. There aren't really a lot of big blockchains today that rely on SGX as their trust assumptions, even though a few years ago there were some discussions of such things. I think Oasis was one of these blockchains, but this hasn't quite worked out this way. Probably because so I don't know exactly why, but I think that the security issues and the trust assumptions there might be problematic. So now we come back to fraud proofs, or we get to fraud proofs, also known as things like optimistic solutions or roll-ups. These are examples of this kind of technology, and this is it's a new and interesting. So it's somewhere in between. Naive replay and reputation-based, but something a little bit different. So the way the system works is, so in the reputation-based system, remember we had this notion of auditors, and there were we said that there was a subset A of auditors. And in the naive replay world, we had this world of end users, and they were all supposed to run. Now, these auditors in the reputation world, the auditors were selected, I don't know by what, by the government or by some trusted party, right? If you look around in your banking industry and you ask, why is it these people who are inspecting it and not others? The answer would be that they come, they were selected by society by some trusted process. They went to law school or to accounting school, they got credited, they worked their way through a system where the reputation is very much important. So in fraud proofs, the way, and we also have, T is the amount of computation, and D is the amount of data. So now in a fraud proof based method, we what we do is post all the data for everyone to see it. So this is D. And all users are going to read this data and keep it. Now, the second thing is anyone can be an auditor. So we're not saying, you can be an auditor and she cannot, or vice versa. And anyone can choose to become an auditor. And we have this arbitration process for for fraud claims. So what does this mean? It means that we have, we have the state of the system as 0, and then suddenly the state S1 appears, and there's all this data that everyone sees. Okay, now presumably someone has moved this, has done this computation, and we are assuming that all the auditors are running the computation. So everyone's running time. All the auditors are running for T steps and checking it out. Now, one of them finds a fraud. And then what we have is, so there's some problem here. So someone cries out, and now we have a process that costs, and the rest of the users are gonna sort of serve as the jury for this. So we're gonna have a process that takes N. Each user is gonna run a process that takes log T steps, in which the auditor that cries out that something is a problem and the entity that has suggested to move to state S1 fight it out, and they do what's called binary search. So the auditor that cries foul says, okay, tell me what was the state of the system at the point after exactly T/2 steps. And then based on that, the fraud claimer can go to either the upper half or the lower half and recurse on this. And after log T steps, everyone who's watching this process can agree as to what happened and whether there was a fraud or not. So the difference from the reputation-based system is that anyone can be an auditor. And we also, for this to work, we need all of the data to be posted. And then we have this very efficient arbitration process for fraud claims. So the good things about this is that this is more efficient because, certainly if there's no fraud, then it is very efficient. You only have A times T computation, which is pretty much as in the reputation-based system that was very efficient. And only if there's a fraud, then you have this additional cost paid by the users of log T. Okay? The problems with this are that, first of all, there is this big question of how to incentivize properly the auditors. And this is a question that is still, under a lot of active research, and I don't quite know what the best answer is in terms of game theoretic. And what are the numbers that come out? So, for instance, think that you have again $1 trillion sitting on this system. So now these $1 trillion could be moved to the pockets of someone. So there's $1 trillion incentive to misreport and violate computational integrity. The hope is that this won't happen. Now, why won't it happen? You have A auditors. So sorry, this is $1 trillion. Okay, so you have $1 trillion. Now, if the set of auditors is very small, maybe they can be bribed to play along and sort of just shut their eyes, and or maybe they can collude together and violate this thing. So you have to incentivize them and pay them. You have to pay the public sufficiently enough so that the set of auditors on an ongoing basis is very large and even has an incentive. So as the size of the computation T grows and grows and grows, you're going to need more and more computational resources to follow what's going on. And now the system has to incentivize this. So this is one big problem with it, just figuring out how to efficiently incentivize the auditors. And a second problem is the one of finality, which, even if you figured out correctly what is the finality, and then you have something that is called capital or general or, state inefficiency. Because we have to allow this process of fraud detection and arbitration to be carried out, we need a relatively large period of time until people can know that the state S1 is really, really final and no one's going to contest it. And because of that, you have this indeterminacy that is pretty long in blockchains. The statement is that it should be around 1 week. But again, this 1 week is, to best of my knowledge, not really based on on numbers. And like, again, this question of the trillion-dollar question, how much of it goes where, and why is it that 1 week is enough? This is an unresolved question these days. Another problem is that of privacy and the fact that all users need to read the data. So if the data is large, then the users, each one of them needs to read this data in order to be able to follow the arbitration and serve as a jury. So there's also this problem of privacy now, because everyone sees the data, and there's in terms of efficiency, it is, if you compare it to naive replay, the cost was n times t and no privacy. So that's really bad. So here we have the same no privacy, but we have slightly better running time for the public. Reputation-based was much better. It was a times t, and you have privacy, which is much better. And here we are somewhere in the middle, but for this unresolved question of the capital inefficiency and how do you properly incentivize the auditors. So this is the fourth method. And now I'm going to ask again if there are any questions. Good, so there's one question. Okay, a minor question by Bent. On fraud proofs, I guess that the program is made public as well as the data. Is this right? Yes, that's a very good question. So in all of these solutions, we are going to assume that the program is known to everyone. Now, in the case of reputation-based systems, if you think about your bank, this isn't actually the case, right? We probably don't know what are the computer programs that our banks are running. We entrust actually the auditors also with this. But for the purposes of this talk, certainly in the context of the other three solutions, two solutions at least. Okay, so under naive replay, everyone knows the program. Under the optimistic or fraud proofs based, everyone knows the program. And under the trusted execution environment, well, if you want computational integrity, then it better be the case that you know what the program is. Otherwise, someone might slip into the program, something that says, okay, if the ID originator of a certain transaction is me, then I can get to move all funds to my account, and we don't want that. Okay, terrific. So now we're going to discuss, as I said, I am biased. So now we're going to discuss what, according, well, my biased view is actually, I think, the optimal solution. And these are validity proof based solutions. So also known as ZK rollups. Starks are part of this. You also have things like snarks, and there are various other terms that fall under this characterization. There's things called validium. These are all various phrases and ZKPs are sometimes used. Okay, so and what we use here is really a bunch of math. That, as I said, we're not, but for saying that there's math involved, I'm not going to explain how it goes. So we have this state as 0, and we have the program. And then whenever you move it to the state S1, you have to must provide a proof. And everyone's going to be checking that proof. So a proof is what you think it would be. It would say something like this. So we want the proof to have the following. So correct statements or transitions, correct transitions have proofs that are deemed to be correct. And incorrect transitions And here I'm have no proofs. So I'm slightly cheating here from a mathematical point of view, but this is roughly what goes on. Have no proofs. So this is what we would like. And now we have this mechanism that is called a verifier. It's a piece of software that checks proofs. And it says, it says either a proof is good for a certain transition or it's bad. So we have a verifier that is a piece of code that can check a proof and say if it's good or bad for a certain transition. So what's going to happen is that the users run verifier. And you have one entity running the prover. Now, the time that this takes, so let's see. So you have one prover. Now, it depends how much time it takes to generate a proof, but let me tell you that generating a proof takes roughly t times the logarithm of t. So this is for generating, this is proof generation. So one party does this. And then the other users, so there are n users, there are many of them, they have to run the verifier. Each verification costs roughly logarithm of t. So this is verification. And proof systems, or ZKPs, that have this property, that proof generation takes t log t, and or quasi-linear in t, and verification takes log t, these are called scalable proofs. And those are the ones that I like best, and Starks are such. So the S in Stark actually stands for scalable, which means that the prover takes time t log t, and the verifier takes times n log t. Now, what have we gained from this? So what are our trust assumptions? We trust the math. And I'll open here. There are various math and crypto assumptions, and there are various flavors. I have a crowdcast actually that talks just about this topic, about how different mathematical and cryptographic assumptions lead to different flavors of proof systems. The TLDR there is that actually the variant that we use in our systems, the Starks, or a lot of them, they have a lot of very good properties, like very lean cryptography. They're very efficient. They're post-quantum secure, and so on and so forth. But there are many, many flavors of proof systems that have different mathematical assumptions. And then you have to place your trust in the math that underlies it. Some of them, though not Starks, some Snarks also need a trusted setup. But I actually, when we talk about Starks, there is no trusted setup. So I'm just going to put an X on that, because in the case of Starks, you don't really need a trusted setup. All you need to trust is the math. And now, again, if you go back to this setting where you imagine that there are, trillions of dollars sitting on this system, and you ask, can someone cheat and move, and move you to a state that isn't good? So the answer to that is no, you can't really. Even if this is, the combination of all the superpowers of the world with all of their computing power, assuming, if you assume that SHA-2, for instance, has no one knows a pre-image, is, so we say, collision resistant, then even the strongest entities that we know of in the world with all of their computing power cannot convince the public to move the state of the system into something that is that doesn't have computational integrity. So yeah, sorry, and this is number 5. So this was an outline of the 5 different methods for computing or dealing with computational integrity and simulating the case of a trusted ideal functionality. So let's see if there are any questions, and if not, I'll just summarize briefly how these different methods compare, and answer some final questions. So any questions? Okay, cool. So I'm going to now just, I am now going to just summarize what we had there. So let's summarize. So we had naive replay. This was number 1. Here we had reputation-based. You know what, I'll give it a little bit more space. Let's put here 2, 3, 4, 5. So here we have reputation-based, you know, banks. Here we have the trusted execution environment, SGX. Here we have fraud proofs, like optimistic rollups. And here we have validity proofs, like Starks. So what do we trust? Let's see if I can, I wonder if I can have like a line. Okay, sorry folks, you're gonna have to bear with my horrible handwriting. Okay, so here we trust nothing, which is really great. So this is, I don't know, let's draw a heart. This is amazing. Wow. Here we have to trust the auditors, which are humans. Humans, they're very, very problematic, right? We are unhappy, very unhappy. Here we have to trust hardware producer. And you know, the hardware itself, that it can't be broken. Again, I'd say that we are very dubious whether we can trust it, maybe even sad. Then we have the fraud proofs, where we have, so it's like half naive. Oh, sorry. We're here in the, who do we trust? Well, I would say we have to trust the game theory, incentives. And my face to this would just be that I am sort of, you know, I just don't quite know what this exactly means. Like, you know, well, it's, you know, how much time, how do you incentivize, so on. Here we have to trust the math. And you know, for one, I'd prefer math any day over. So this is trust. Then we have efficiency. So like, how much computation time does the universe have to pay? Then we can also add here maybe privacy. Does it have? Well, let's start with privacy. So privacy, this doesn't have privacy. So again, we are very sad. Reputation, well, you know, we are maybe happy because, you know, the auditors can, you know, auditors see, who knows what they're going to do with it. Here, well, under the assumption that it works, I guess we're happy. It's just that, you know, we don't know if it's going to work. Here, we are unhappy because everyone needs to see all of the data. And here, again, we are happy because only the operator of the computation can, you know, is the one that will see it. And we even have zero knowledge that gives us a very high grade mathematically of privacy. So in terms of efficiency, here, the world has to pay n times t, which is really, really bad. So that's unfortunate. Here, we said that we have the auditors paying t, which is really, really good because the auditors are a small group and only they have to run the computation. In the trusted execution environment, it's even better because there's just like one party that has to run time t, and everyone else has just to verify signatures. So we have n times something that looks like log of t. And you may ask, why is it at least log of t? Well, I'll leave that as a food for thought. Why is it that checking a signature must take at least log t steps? So I'd say we're also pretty happy. Logarithm of a trillion is a pretty small number, so it's not that bad. I mean, we're slightly less happy, maybe. Like here, we're very happy. Where is it? No, sorry. Okay, I don't know. In both of them, we're pretty happy. In the fraud proofs, we have A times T because all the auditors have to run it. And then the rest of the users have to read the data and process, log T in case of a fraud proof. So it says, okay, it's slightly worse than the previous two things, but, let's put it a moderate smile, a smirk. And then here we have one party generating the proofs, which is T log T, and then everyone else does n times log T for verifying it, which is also, I'd say, pretty happy. So summarizing, and I said I'm very biased in this thing, I ain't affiliated with Starks for nothing, but this is my prescription for the world. This is the best way. Going back to, for instance, Paul Krugman and the conventional folks and saying, why don't you use reputation? Well, reputation ain't so bad, but you have to trust the auditors, and it's not more efficient than validity proofs. And there you don't have to trust anyone, and you have the privacy, and it's guaranteed by math and not by a bunch of friends of economists. So now I'm going to answer questions, and okay. Just one second. First question by Nomad. Is it possible to combine the validity proof method and the fraud proof method? Oh, wait, went down here. Let me start answering. Is it possible to combine the validity proof method and the fraud proof method to obtain the two advantages? I'm not sure what you mean by the two advantages. If you go back here, I mean, what is the advantage of the fraud proofs? I'm not sure I see it. Where is it better? It doesn't have privacy. It takes more time because it's n times d plus log t, and it's a times t. Oh, I see. If a is less than log t, then you could argue, well, then you maybe, I mean, you also have in the second term for fraud proofs, you have, so I would say that under most cases, in the validity proofs world, you both have privacy assured. You don't need the users to read the data, and you probably have more efficient running time for the users and for the entities who are tracking the system. So I wouldn't advise it, but I guess that it requires more thought. I think that theoretically you could combine the two in various ways, but I'm not sure what you would gain by that. Okay, but needs more thought. Okay, second question. Bent. I guess for validity proofs, wait, sorry, let me go up, the one with the 2 votes. Okay, also by Bent. You gave some nice theoretical scaling equations. Is there any way to compare these in some practical way? Are there any hidden constants or practical considerations? Terrific question. Of course, I was hiding a whole bunch of stuff underneath. Yes, there are many, many practical considerations and hidden constants. Talking about those would take a very long time. I should say that in the Crowdcast, there are a whole bunch of lectures that address various aspects of building validity proofs, because that's where we are focused on. Surely there are many, many constants and practical considerations. Yeah, definitely, totally right. that would be the topic of some other talk, and probably a lot of research has to be done in comparisons and whatnot. Yes, but there are many hidden constants and practical considerations. I mean, we will see these various things playing out in the world. I mean, the world is dominated by reputation-based systems, right? The whole financial world operates in this way. Naive replay is blockchains today. We can see it working out. Trusted execution environments are, I think, not that much used in the well, okay, I don't know, but they are also efficient if you trust them. The problem with them is the trust assumption, not their efficiency. And then, Starks are out there operating a bunch of systems, and you'll see more of them soon. And fraud proofs are also, I mean, there's Arbitrum and optimistic rollups, and there'll be a lot of comparisons practically there. So yeah, we'll have to wait a little bit and see how it goes. Okay, next question by Ben. I guess for validity proofs, the users have to trust the mathematicians and CS gurus. I trust you, thank you. But I trust you, Ben. But for example, a tech distrusting politician may suggest that we not trust the math. I guess this is insoluble. So I think it's a terrific question. And this question applies to all of these 5 things, right? Talk about, well, even for naive replay, because at the end of the day, the computations are pretty complicated and the algorithms, and in the middle, there are compilers and hardware and routers and everything. So the same politician could argue that, and by the way, would very rightly argue so, because actually, any sufficiently complicated piece of code has a lot of bugs in it, and some of them may have been inserted there on purpose and some not. So even the simplest of the solutions, the naive solution, which is naive replay, could be attacked for being maybe not trustworthy in terms of the math and the implementation. Certainly that's the case for reputation, for trusted execution environment, for fraud proofs, and for validity proofs. Yeah, so someone could argue this. But I think the discussion and comparison here should, I should have made this as an assumption. We are taking each one of these, just as we assumed that the computer program has no bugs, we will also assume that everything is working there as intended, meaning that the hardware doesn't have bugs, the fraud proofs as a mechanism doesn't have a bug in its implementation, and so on and so forth. So yeah. Next question by Yaakov. Is there a bound on the T log T prover time? Is there an impossibility result for T log T of PV respectively? Okay, terrific question. So here's what we know, and we know very little in terms of lower bounds. Okay, we know that the running time of the prover must be at least T. Okay, otherwise there are various things that would break. Similarly, we know that the running time of the verifier must be at least log T. Okay. Now, the question of whether a prover can run in time T log, so we only have this factor log T for the prover that we could ask, could it go down? Because the verifier cannot go below log T and the prover cannot go below T. So you have this multiplicative factor of log T. This is a tremendous, amazing theoretical problem. We don't know the answer for it, but it's a terrific question. Okay, last question that we have now. If you want to hand in your questions, this is your last chance. Defiant question. Why are we not yet using validity proofs at a large scale? Oh, yeah, I love this question, of course. Thank you, Giuseppe, for putting it there. Yes, we should use them much more. Well, the answer is that, okay, validity proofs were first suggested theoretically about 35 years ago in 1985. And as a rule of thumb, mathematical breakthroughs in computer science take roughly 3 decades till you start seeing them in practice. Okay, and this is true for error correcting codes in general, and it's certainly true for this technology. So only about, by this rule of thumb, only about like 5 years ago, you started seeing proof systems at, just going out there. And then it takes time, these things. we at Starcore are working very hard. There are other amazing teams out there, Aztec for one, the Zcash team. They're working very hard to make validity proofs work on a much large scale and everywhere. It's going to take some time, yeah, but they're going to get there. I want to mention one other thing, which is that the reputation-based system, as articulated by Paul Krugman and a lot of economists, first of all, they're very happy with the reputation-based system. So they don't have that much of an incentive to change it. And, for those who are part of the group of auditors and those running the system, certainly the reputation-based system is a very profitable one. They are incentivized to protect it. And most of the conventional world works that way. So it's going to be a hard uphill battle. Thank God there's blockchains to help us in that and disrupt it. Okay, Bent, is there a way for validity proofs to enable layer 1 blockchain scalability and not just layer 2? Yes, of course. All you need is, for instance, Bitcoin to add an opcode for Stark verification. And Starks are very much in line with the ideology of Bitcoin, because there are no trust assumptions. The math is very trustworthy. There are no even number theoretic assumptions. It is post-quantum secure and so on and so forth. So I think, and it doesn't have to be Bitcoin. Any blockchain that is layer 1 and wants to add a Stark verifier as an opcode, and it doesn't have to be even a Stark verifier, because to verify Starks, all you need is to verify paths in a Merkle tree and do some linear algebra over a finite field. So modular linear algebra. As long as you accept that into your layer 1, yeah, then you have immediately layer 1 blockchain scalability. Yeah. So it's really up to the protocols to decide that they want this, and I'm sure some of them are going to want this. Okay, Nomad. Validity proof cannot treat the state due to privacy, not simple token. I'm not sure I understand the question. The question is, validity proof cannot treat the state due to privacy, not simple token transfer. I'm not sure I understand. I think validity proofs can update. I mean, do you want to clarify that, Nomad? Maybe add a few words you can edit or comment. I'm not sure I understand the question. So I'll just wait a minute or two just to see if you want to clarify the question. You can put it in a comment or edit. But I just want to say that if you want full privacy, for instance, Zcash style, then you can do that with validity proofs as well, and at scale. Basically, you move to a different kind of state of the system, where the state of the system does not represent the information itself, but it validity proof cannot treat the state. A validity proof is something that you can. So the way, if we go back to this. One slide back. What validity proofs, the way you see here, you move, right? You're gonna, I mean, you do move from state S0 to S1, but you must provide a proof. So the way you work with validity proofs is you use them to support the correct transition of your state. Okay, so I want to thank everyone again. I want to mention that if you want to see or learn a little bit more, wait, I see there's a question. How can I trust the math being a normie? Is it a reputation-based system again? It is a reputation-based system again for me. More a statement than a question. Well, my answer to that is, I mean, it's a great question. And, back in the day before COVID, I used to board airplanes. And airplanes, there are these big metal things that go way up high, and they can fall down, and I could die. So I trusted my life and whenever I drive a car, certainly the new ones that have a bunch of computers in them and algorithms, but even the old ones, I trust my life and base it on technology and math, ultimately, right? Because physics is math that I completely do not understand. Now, why? How is it? So, and it's a deep question. I guess the process that happens to all of us, right? And even if you were to understand this very particular piece of math, there are other aspects of the bigger system, how networks work, why the internet is safer, whatever, that I'll never be able to understand. So I guess there's this social process that we go through where a new technology comes in, and we rely on various experts to examine it and vet it, and they're peer-reviewed, conferences and journals for that, and you also wait for bugs to emerge or people to talk to. So it's this process that takes quite some time. But that's how humans as a society in general have become accustomed to and comfortable with a lot of technologies, in which we base our life. I'm fortunate here to have been vaccinated a few months ago I injected some RNA things into my body, some new technology. I completely don't understand it. I have no idea whether it's not going to cause me any diseases. So ultimately, you have to rely on your trust in some other experts. It's no different here. But I'm just saying this is part of being a member of the modern society. That's we see it all the time. Okay, so terrific questions, and okay, how can I contact you for asking about your previous seminar? Okay, so what I'm going to do is I'm going to also post here in the chat. First of all, well, I'll just put my my email. But I'm also going to, once we end, I'm going to post here just the link to my Crowdcast events, and you can go there and see all of the previous episodes. Some of them had amazing, speakers from the outside that you should go and watch. Vitalik Buterin, Avi Vigdorson, the recipient of the Abel Prize for 2021. Justin Drake, Arthur Brightman, Andre Cronje, and so on and so forth. Okay. So thank you all very much, and see you in 3 weeks or a month on our next Start at Home.